Okay, this is a practice test for Quantitative Methods 3341. This is going to cover chapters 10, 11, and 12 in the Hawks Discovering Business Statistics book. And we're just going to jump right in. Let's get a big blue here. Question number 1. This newsletter believes that over 62% of the readers own a Rolls Royce. This is the this guy right here is our statement of interest. Okay, that's where our hypothesis is going to come from. For marketing purposes, a potential advisor wants to confirm this. After performing a test at the O2 level of significance, an advertiser decides to reject the null. So there's not a lot of math here for you to do. This is just to see whether or not you understand what the hypothesis test kind of looks like. So we can come down here and draw or write out our hypotheses, and the one we're interested in is hypothesis 1. That's the one we want to prove. What does this guy want to prove? He wants to prove that over 62%. This is one of those read the questions right deals, because it says over 62%. That's where you might get some confusion there. So that's our mu. Mu is that 62% of the readers have a Rolls Royce. And this is going to be the exact opposite, which is less than or equal to 62%. You then find out that he or the marketing advisor, the marketing firm, has rejected the null. And so we reject the null, and ostensibly there is enough evidence to prove that 62. So we look at the two questions. There is not. This is one of those. So the correct answer is A. There is sufficient evidence at the O2 level. Simple question. It's not necessarily intuitive. Nobody's trying to trick you here. You're assuming that they do the test correct. The advertiser does the test correctly, and so just think it through and make sure you have the right answer here. Okay, let's scroll down to question number 2. All right, so I kind of modified the screen a little bit. If you see it jump, don't freak out. So let's continue. Let me go back and grab my colors. All right, let's continue. The director of research and development is testing a new drug. She wants to know if there is evidence at the 0.05 level that the drug stays in the system for less than 305 minutes. Well, I'm going to do my cheat sheet like I always do. Alpha is equal to 0.05. The drug is supposed to be in the system for 305 minutes. That's going to be my mu. This is what the company is telling me. And then we're going to go out and test whether or not that's true for a sample of 68 patients. Sample of 68 patients. That's a sample size. Whoops, it's not my X bar. That is a sample size of 68. The mean time displayed at 299 minutes. So we take a sample of 68 people and we take their mean, and it was in the system for 299 minutes. Assume the standard deviation is known to be 23. So we know the standard deviation of the sample is 23. Okay, so what are our hypotheses? The hypothesis is whether or not the drug stays in the system for less than 307 minutes. That's what we're trying to prove, and we're running our test to prove whether or not that's true. So we want to prove that that's the case. I want to know if the mean is equal to, nope. I want to know if the mean is less than 307 minutes. Not less than or equal to, but less than 307. So my null hypothesis is the exact opposite. Mu is greater than or equal to 307, and that's the one we're hoping to reject. Okay, step 2, enter the value of the z-test. Well, my z is going to be equal to x bar minus mu over standard deviation, but here we're taking it from the sample. We don't know what the standard deviation is for the entire thing, so that's going to be s over the square root of n. All right, so this is simple math. We've done a lot of these. 299 minus 307. At this point, I'm just substituting and doing real easy math. 23 over the square root of 68. And I'm going to bring out my fancy calculator here. Ta-da. Let's clear that. I'm going to do the square root of 68 first. 68, where's my square root? there's my square root, and that's 8.25. So I'm just going to write a little note here. That's 8.25. This guy is equal to 8.25. Calculator. 23 divided by 8.25 is equal to 2.79. So my denominator is going to be 2.79. Let's give ourselves a little bit more space here. Let's scroll that down. So let's go back. So this is going to be equal to 299 minus 307 divided by 2.79, which that is equal to what? Negative 8 over 2.79, and that is equal to negative 8 minus 2.7 divided by 2.79. So 8 negative divided by 2.79 is equal to 2.87, or negative 2.87. That's my z. Was that correct? Yes, it is. There's my answer. So traditional z calculation. Just remember that this is going to be standard deviation of the sample. Okay, number 3. Specify if this test is one-tailed or two-tailed test. Well, I'm working on this guy right here. Step 3. Step 3, one-tail or two-tail? Well, I can tell it's going to be a one-tail test because it's going to be either greater than or less than, right? And so we don't require a lot of time here, but let's go through it anyway. I'm going to end up with this curve that looks something like this, and there is the mean here was whatever it is. Actually, it's 0. 2.87, negative 2.87 is, actually it's much, much further. It's going to be over here somewhere. Negative 2.87 is over here, and I want to prove whether it's less than or not, and this is otherwise. If it comes this way, I'm going to reject, and over here I'm going to fail to reject. So it is a specified test is one-tailed or two-tailed. It is a one-tailed test. And there it is, one-tailed test. Okay, 4. Enter the decision rule. We're going to reject if h sub 0 is what? So this is asking us for our critical value. Okay, that's what the decision rule is asking us to do. Let's get that out of the way. So how do we know what our critical value is? Well, we base our critical value based off of alpha. What was our alpha? Alpha was equal to I wrote it down, 0.05. 0.05. So there's a couple of different ways to do this, and we should have some of these memorized. Let me pull out the book here real quick. Bring this over here, and let's go find, hello. How come it's not letting me get in here? Maybe I can do it off screen. My computer seems to be frozen. But at alpha equals 0.05, some of these we just have memorized. And I know that at 0.05, the critical value is equal to negative 1.645 for a one-tail test. Okay, so let me bring that back over here. That's really hard to see, but we're going to just kind of play with it a little bit. All right, so there's two ways to do this. We can go over here and look for 0.05 inside the screen. I know you can't see it, but it's right about here somewhere. And if I follow this 0.05 out to the left, I get 1.64, and that's how we can walk back the traditional table to figure out that you find the percentage in the middle, and then we walk out to find the other one. And I'm back. So yeah, you grab the percentage from the middle here, and then we go out to 1.6 and then up to 1.64, and that's how we get that. Conversely, if we come over one page, One page. One page. If you go over one page, down here at the bottom of this particular page, where's my zoom? You're going to have these critical values of z. Noting that, you know, this is alpha divided by 2 or alpha divided by 2 on this side. And so here we have, you see the 1.645, which is kind of where we want to be, but it has it at a level of confidence of 90. Now, if we come over and you turn around and say you have a one-tail test, the way we have a one-tail test, then it's this 1.65 then drops down to the 0.95 because this side is open, so to speak. Okay, I only then care about the other one. Here's my 1.65 on a one-tail test. I think you'll find when you get into research, and a lot of the research that's out there in the future, you'll see two-tail tests more often than the one-tails. In this case, we have a one-tail. You want that 1.65 to be on that side. So hopefully that's where you get your critical values. Shouldn't be much different than what you've done in the past. So we are going to reject here if negative 1.645. And don't forget the negative. Don't forget the negative. So that's our decision rule. The decision rule is our critical value. What is the conclusion? We can reject the null, or we can fail to reject the null. Well, our critical value is, we're interested in negative 1.64, and anything on the left-hand side is going to get rejected. We come up and look at our z. Z is negative 2.87. Negative 2.87 is over here somewhere, negative 2.87. Therefore, we reject the null. Correct answer, reject the null. All right, so not a lot of huge stuff there. Let's look at question number 3. The director of research and development is testing a new drug. She wants to know if there is evidence at the 0.025, alpha is equal to 0.025, that's really small, that the drug level in the system is in the system for less than 393 minutes. I'm going to change this question so we don't have two of the same thing going twice. But the same question here, less than 395 minutes. So mu is equal to 393 for a sample of 17 patients. Oh, maybe it's not the same question. N is equal to 17. The mean time the drug stayed in the system was 387. X bar is equal to 387. With a variance, not a standard deviation, but a variance, S squared, of 625. Maybe it's not the same question at all. Let's start at the beginning with the beginning. State the null and the alternative hypothesis. Again, there's my H. There's my alternative. Let me make it visible. Thank you very much. Tab it over so that it makes sense. All right. So just like before, this is the guy we're trying to prove. So this is going to be that mu is for less than 393, less than 393, and my H sub 0 is going to be the exact opposite, greater than or equal to 393. And those are there. We're good. We're good. All right, find the value of the test statistic. The test statistic. What is our test statistic? Our test statistic is going to be, well, this is a little different here. And why is it different? It's different because we have a smaller sample. We don't have 30 in our N. Therefore, we're not looking for a Z. We're looking for a T. And right off the beginning, we're going to make a calculation based off of trying to find that T. The good thing about T is that it's almost exactly the same calculation. X bar minus mu over sigma divided by the square root of n. Yes, divided by the square root of n. So it shouldn't be that much different, and we have all of these. So we have X bar is 387 minus mu is 393. Let me change the angle of this thing. Maybe I can draw straight. should at least try. 393, where S, but we don't have S, we have S squared. And S squared is 625. So we got to make sure we go back and calculate the S. Where's my fancy calculator? 625 square root is 25. Go figure. Where S is 25, there's your little trick question part. 25 divided by the square root of n. What is the square root where it is n? N is 17. So I'm going to come back again and get my fancy calculator. Let's give ourselves a lot more space here. Bring back the fancy calculator. Bring back the fancy calculator. There it is. 17 square root is 4.12. This is equal to 389 minus 387 minus 393 is 6, negative 6 over 25 divided by, what was it? Fancy calculator, fancy calculator. 4.12. 4.12. At this point, it's just math. Let's do the one on the bottom first. 2.25 divided by 4.12 is equal to 6.07. So this is equal to negative 6 over 6.07. And that should give us something like 0.9 something or other. 6 divided by 6.07 is equal to 0.99. What do we have over here? Oh, there it is on the top. Okay, good. So this is 0.990 negative. And that's our correct answer. All right. The whole point of Chapter 10 is not for you to do, Stats 1 stuff over and over again, but to test what to do with those numbers once you get them. So here we ask if this is a one-tail test or a two-tail test. Our h sub a or h sub 1 is not the equal sign, but the dots, the colon. That mu is less than 393, I think it was. This is why I have my cheat sheet, 393. Excellent. Mu is less than 393, and because this is a less than sign as opposed to the other one, I know it's a one-tail test. Check. Next. Step 4. Determine the decision rule. Decision rule, again, is critical value. So here we go to the alpha. Alpha is equal to 0.025, which is just half of 0.05, right? But this is, again, a one-tail test. So we go back to our sheets. Let me see if I can do a better job this time. Yeah, it's finally working. Statistical tables. Go forward one. Here's my cheat sheet. I'm going to zoom in this time. And this is a one-tail test. Happens to be on the negative, so that makes it easier. It happens to be, you'll see over here, that happens to be on the left-hand side, so it makes it real easy. 0.025, 0.025, 0.03, 0.023, 24, 25. Boom, right there. So this is going to be negative 1.9, and whatever's up here at the top, negative 1.96. Similarly, I can go to my little critical values cheat sheet on the next page that has 0.095. But remember, this is, in this particular chart, we're looking at alpha divided by 2. So I'm going to take this to whatever half of that is, 0.975, right? Because that's alpha minus 1 minus alpha. And I'm going to grab that 1.96. Don't forget, this is a one-tail test, and this is describing a two-tail test. Okay? Your question is a one-tail. This guy is a two-tail. Don't get confused by the critical values here. If you have a doubt, go back and use the big tables to do that. So we find our critical value is 1.96. Oh, that's not right. What did we do wrong? Well, let's go back and do it from scratch. Alpha is 0.025. Alpha is 0.025. That's not what I want. Alpha is 0.025. Let's go back a page. Alpha is 0.025. 0.025. It's a one-tailed test. 1.96. Why is this telling me? Oh, because it's a T. Huge, huge difference. Okay. All right. That's a very, very critical error. And as you can tell, it's one that happens relatively common. So, glad you saw me make that error. So we need to go back and grab the critical values of T. Critical values of T. And let's go ahead and zoom in. All right. So what do I need from T that I don't have in Z? It's the degrees of freedom. What is our total degrees of freedom? Degrees of freedom is n minus 1, right? So if I go back up to my cheat sheet, degrees of freedom is equal to n minus 1. N is 17, so that's 17 minus 1. Degrees of freedom is 16. So let's go back down to critical value. So here it's a very good, very classic mistake made by folks all the time. In this case, we are doing a t-test. At alpha is 0.025, where degrees of freedom is equal to n minus 1, 16. Big, big deal. Let's go back to our table. So here's my degrees of freedom. I'm going to go down to 16. I'm going to see how low I can get this. Can you see that? I don't think you can. Here's my 16 down here at the bottom. And now I got to find 0.25. And I run down here to 16. And my critical value is 2.120. 2.120. Negative. There it is. There it is. Negative 2.120. Again, right from the beginning, I said, oh, it looks like the exact same problem. It isn't, because here we're looking for a T, not a Z. We don't want the Z, we want the T. If we want the T, don't forget to go back and calculate degrees of freedom, which in this case was what, 16, n minus 1. All right, so that question is probably going to stay, or one just like it. Step 5, reject or fail to reject the null hypothesis. Okay, so we have our curve. When in doubt, draw it out. We have our curve. The T looks very much like the Z, right, with a mean of 0. And out here we have a critical value of negative 2.120. And anything to the left-hand side, I'm going to reject. Everything on this side, I'm going to fail to reject. We go back and figure out what our T is. What was our T? Didn't we calculate one? Yes, we calculated a T. This is a T, not a Z, and that's negative 0.990. Negative 0.990 is going to be in here somewhere. Negative 0.990. Our critical value is bigger or has more magnitude than negative 0.990. Therefore, we fail to reject. Fail to reject. Okay. Next question. Whew. The manufacturer of chocolate chips would like to know whether its bag filling machine works correctly at 405 gram setting. That sounds an awful lot like a mu. That's what the machine is supposed to be. 405 grams. It is believed that the machine is overfilling. Dun, dun, dun. 26 bag sample. I like that. N is equal to 26. Is that at least 30? It's not. What am I thinking? Has a mean of 411 grams. So the sample has an average of 411 grams with a standard deviation of 15. 15. Assume the population is normally distributed. Check. Is there sufficient evidence at 0.01? alpha is equal to 0.01, that the bags are overfilled. So we have to ask the question. So the question that we're asking, we don't have to ask the question. The question that we're asking is, how come that didn't work? The question that we're asking is, thank you, are the bags overfilling? How can I do this? Thank you. Are the bags overfilling at greater than what they're supposed to be? What are they supposed to be? They're supposed to be 405 grams. And so I want to test if the mu is greater than 405. Therefore, my null hypothesis is that it is less than or equal to 405. The correct answer, there's probably more to it. Yes, there is 405. All right, so we have our null and we have our alternative hypothesis. Find the value of the test statistic. Well, what is our test statistic? How do I know if I'm using a Z or a T? If I'm using a T, if my sample size is small, in this case, n is equal to 26, it's close to 30, but it's not 30. I'm going to play it on the safe side, and I'm going to go with T. 30 is our decider. I'm the decider. And let's go look at how we calculate the T. Not a big stretch from what we were doing before. X bar minus mu over standard deviation divided by the square root of n. And that looks like, where's our X bars and stuff? 411 minus 405. 411 minus 405 divided by 15 over the square root of 26. 26. Again, a lot of this is math. We're going to bring out the fancy calculators. 411 minus 405 is a positive 6 over 15 divided by the square root of 26. The square root of 26 is easily calculable using our fancy schmancy calculator. Pull that out to the side. Clear. 26 square root is 5.10. I can throw that into memory if you guys are big fans of memory. And then I can take 15 divided by recall memory. Note the 5.12 pops right back up. And I equal that to 2.94. So this is equal to 6 over, I don't remember what it was. So we'll just put the 2.94. 2.94. And that is not correct. Calculator. 26 second square root, 5.10. Put that into memory. Let's go back up here, go the long way. 5.10. 15 divided by 5.1 is equal to 150. Okay. So this guy is equal to 150. That's not right. Okay, so I went back and worked this problem a couple of different times, and I'm going to go with the fact that this is a typo. And our solution was 2.94. Or you know what? Let's just do this again from scratch. We'll just do it. Let's do this calculation. So let's erase all of this guys here, and let's build it again. And I think you're going to find that we're doing this correctly. So 411 minus 405 is 6 over 15 divided by the square root of 26, which we have done like 10 times. Where's my calculator? We're going to do it one more. Put this over here on the other side. 26 square root is 5.10. So this is 5.10. And this guy is 15 divided by 5.10, or it's like 5.99999, is equal to 2.94. So this guy is equal to 2.94. Therefore, scroll down some more. This is 6 divided by 2.94, and that equals 6 divided by 2.94, 2.04. It is right. 2.04. I must have just stopped here and got it wrong. So this is our t statistic, and it is correct. 2.04. Excellent. Excellent. I'm a lot smarter than I look. All right. So specify if the tail is one-tailed or two-tailed. This, our H sub A is that mu is greater than whatever the bag fill was. What was the bag fill? The bag fill was the mu, 405. The bag fill was greater than 405. Therefore, it is one tail, right? It's not equal to, it's either greater than, it's either bigger than 405 or it isn't. One tail test. Excellent. Find the p-value for the test. And just like we did before, we're not going to make the mistake again of thinking that this is a z. We've been saying it's a t over and over again. So in this case, our t is equal to negative positive 2.04. How do I then go and get the, is that correct? 2.04? Yeah. Well, it doesn't have to do, right. So how do I get the p-value of a test statistics when the t is 0.024? Use range using interval notation. So we're going to look at whether it's one thing or another, and whether it's between 0.05 or 0.05. So we're just kind of, we're going to use the test to do that, and let's do exactly that right now. Where's that test? Here's my t statistic, and in this case I have a t stat. It's negative, it's positive, to put it over here, 2.04, so we can see it while we're working. 2.04, 2.04, 2.04. I have 2.2.2. Oh, but I have a degrees of freedom, right? So what is my degrees of freedom? I have a total observations of 26. So let's go grab our degrees of freedom. Our degrees of freedom is equal to 26 minus 1, or 25. Ta-da. And now I can walk this guy down to 25. Here's my 25. Walk across until I get something smaller than or between 2.06 is what I'm showing. 2.04. So I'm going to be somewhere above 2.06, but I'm sorry, above whatever this previous one is, 1.07, but below 2.06. So let's run this up to the top, and I get a t-stat between, an alpha between these two, 0.025 and 0.052. At that alpha, I get a p-value of whatever is something between that, right? So my p-value is going to be between 0.025 and 0.05. Here we're going to say 0.0260, and I think this is the answer if you calculate it using a calculator. I'll have to double check that. We're obviously using the book. So this is the one, if you're using the tables, this is the answer that you would input, between 0.025 and 0.05. Let's look at that one more time, which might be a little rusty. So what we did is we looked at our t table and we found the degrees of freedom, walked it down to our total degrees of freedom, it's 25, 25, and then we looked at our stat, and our stat's somewhere in the middle here, and it is smaller than this guy, 2.06, and it is bigger than 1.7. So it's going to fall between these two. I'm going to keep the finger, I'm going to scroll up to the top, Scroll. There's degrees of freedom. Here the t-stat is 0.025, and here the t-stat, or the alpha is 0.025, and here the alpha is 0.05. So I'm going to turn around and say, hey, it's somewhere between 0.025 and 0.05. If you do it fancy, you would go and find the appropriate calculator and calculate out 0.026, and that would be an acceptable response as well. Okay, so what is identify the level of significance for the hypothesis test? Well, they have told us in the question, right? What have they told us? That alpha is 0.01. We already know that. It tells us right here alpha is 0.01. So that's just plug and play. The correct answer is that alpha is equal to 0.01. That is excellent. Decide whether to reject or fail to reject on the hypothesis. This question is asking for the exact same thing that the previous question is asking, but it's saying, hey, look, you have an alpha and you have a critical value at some alpha. So we're asking for 0.01. It has to be at least 0.01 or smaller, but our stat falls between 0.025 and 0.05. This guy's bigger, okay? So this is not going to fit. Actually, that's not an appropriate mathematical statement. I'm going to get rid of that. Basically, we are looking for our t-stat. We're looking for our stat. Let me change colors. Black is probably a terrible color right now. We're looking for this to be so far outside that we're going to reject it. And we find that the p-value under 2.04 is somewhere between this one and this one. So it's bigger than this. It's bigger than 0.025. But our scientist has says, I need it to be bigger than 0.01. And because it isn't, or I need to be small, at least 0.01. So it's got to be smaller than 0.01. And because it isn't smaller than 0.01, we fail, reject the hypothesis. What is our critical value? We don't really have a critical value. We have a p-value, and that p-value is no smaller than 0.025. Because they're asking us for 0.01, this is not an appropriate number. We want stuff that's smaller. Smaller is what we're looking for. We didn't get it. We failed to reject the null hypothesis. Okay. Oofa. All right. So there's a lot of data here. There's a lot of numbers. Don't be intimidated. You've seen this before over and over again. So we shouldn't be. Let's pick a new color. Let's work with that blue again. I kind of like that. It's a little too skinny. All right. How's that? All right. So here we have two compounds, 1 and 2. Okay. So we have compound number 1. We have compound number 2. This is going to be a lot easier if you write these little cheat sheets with your notes. There are two different compounds that manufacture car tires. They're designed to reduce braking distances. The SUVs equipped with the tires in compound 1 have a mean braking distance of 72 feet. Mean braking distance of 72 with a standard deviation of 10.6. SUVs equipped with tires using number 2 have a mean braking distance of 74. They seem really close. And a standard deviation of 12.3. Those guys seem really, really close to me. Suppose that a sample of 38 braking tests have been performed. Here's 38 braking tests for each compound. Using these results, I should do it this way because it's for each, right? So I should say n is equal to 38 and 38. Using these results, the test the claim that braking distance for SUVs equipped with tires using compound 1 is shorter than braking distance with compound 2. So in my test whether or not this is shorter than 2. Test whether test 1 or tire 1 is shorter than 2. Let mu be the true mean of the braking distance, which tells us that this is really a sample. That's fine. Be the true mean braking distance corresponding to compound 1, check. And mu 2 be the true braking distance, blah, 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 corresponding to compound 2. So this is mu sub 1, and this guy's going to be mu sub 2, okay? Intuitive, alpha is equal to Alpha is equal to 0.05. So right off the top, you know that we have a test for differences here. We have two groups. We have compound 1, we have compound 2, and we're going to test to see whether or not they're the same. How do we do that? Well, before we get there, state the null and alternative hypothesis. The hypothesis I want to prove is I have two groups. I want to prove that they are the same or that they are not the same. Well, that's not what the question is asking, right? The question is asking to test the claim that the braking distance with tires using compound 1 is shorter than the braking distance. Okay? Don't automatically assume when you get a t-test for differences that you're automatically going to do unequals. We want to know that number 1 is better than number 2. And we're talking about braking, right? So this should stop shorter. So the 72, it's important that 72 is less than 74 because on the surface at least it's stopping shorter. But it's not an unequal sign, all right? That's not what we're trying to prove here. Erase. We want to prove that compound 1 stops shorter than compound 2, which means my H sub 0 is that compound 1 is greater than or equal to mu sub 2, okay? This is a one-tail test. And that can be a little tricky when we deal with two samples because you're automatically going to start thinking that we're dealing with the difference between the two means. Okay, so compute the value of the test statistic. And this is where things get a little different, right? Because at least we know we have at least 30 observations, so we're going to deal with the z. But the z for this guy changes a little bit. We're going to have to do a little bit more math because we're dealing with the means of two groups. This is going to be the mean of the first observation, or the first test, minus the mean of the second test, minus mu, the mu sub 1, minus mu sub 2, all over a combined variance, or a combined deviation. Sigma squared for group sub 1 over n sub 1, they happen to be the same, plus combined sigma squared for the second one over n sub 2, the n's happen to be the same here. And don't get scared, again, this is very, very similar to what we've done in the past, okay? Except that here we're looking at two groups instead of just one group. This is still x bar minus mu over the sigma divided by n, right? In this case, the square root. And notice how we put the square root over the variance, not the standard deviation, all right? And here we have standard deviation, not variance. Okay, we're going to need a lot more space for this guy. Get out of here. All right. So let's erase this so we're not confusing ourselves. All right, so so let's do some plug and play here. Is there a better way to do this? Can I grab this whole thing here? How do I grab this? Let me see if I can figure out how to grab this. Control C. Let's see if this works. I've never done this before. Control V. Oh yeah, it worked. Awesome. And I put it in the wrong place. Let's put it all the way up on this corner. Never done this guy before. This is fun. Let's put it over here somewhere. Or you know what? Maybe I can just drag it out of the way, where you can still see it. Excellent. And let's change colors so that we're so we know what we're doing. Okay, so x sub 1 is the 72. So 72 minus 74. That's my x bars, minus mu sub 1 minus mu sub 2 over the square root of Sigma sub 1 is 10.6. 10.6 squared over 38 plus, not minus, 12.3 squared over 38. Not 6, 38. Okay. A couple of points here. The first thing we're going to do is we're going to note that our null hypothesis is going to make these two guys disappear. So those guys go to 0 right off the bat. And I'm going to, well, we'll just go ahead and do it all together, because why not? Where is my calculator? Here's my calculator. All right, so I'm going to start it in the denominator. 10.6 squared is 112.36. This is going to equal to 112.36. 12.3 squared is equal to 9. That's not true. 12.3 squared is 151. This is equal to 151.9. 0.29. 38 is on the bottom. Let's just go ahead and rewrite this pink equation again. Let's keep it in pink so that we're all making sense. 72 minus 74 is negative 2 on top. So that's good. Square root of 112.36 divided by 38 plus 151.29 divided by 38. So the denominators are the same. I can actually add these together, right? But let's not, you know what, let's not get fancy. Let's just do the work. Let's write it down again. We're going to need more space. This is equal to negative 2 on top over 112 divided by 36. Whoops, sorry. Calculator. 112.36 divided by 38 equals 2.96. So the square root of 2.96 plus, calculator, 151.29 divided by 38, 1.37. 1.37, which is the same as saying this is equal to negative 2 over the square root of 3, 4, 30, 33. 4.33. Fancy calculator. 4.33 square root is 2.08. Ugh. Stupid mouse. Sorry. That one's on me. So this is equal to negative 2 over 2.08. And that finally should be something just close to 1. 2 negative divided by 2.08 is equal to negative 0.96. So our t, our t is equal to negative 0.96. Our z is equal to negative 0.96. All right, this is determine the decision rule. Again, the decision rule is going to be our critical value. Where do we get our critical value from? We get it from alpha. Alpha in this case is equal to 0.05. Let's go back up and double check that. Alpha is equal to 0.05. Awesome. So we go to the book. Grab the book and bring it back over. I can go back to the formula pages. No, statistical tables. Next. Excellent. Now on this side, we're going to do the opposite, right? That was a negative. This guy's a positive. We're going to do a one-tailed test. and figure out, no, it's still negative, and figure out what the percentage is. So we're at 0.05. 0.05, let's go find 0.05, 0.05, 0.05. 0.05 is right about here somewhere, 0.05. So again, negative 1.664. I'll grab 1.64. It's going to be in the middle of there somewhere. Negative 1.64 because it's a one-tail test. So our decision is based off of negative 1.64. You fill that in right here, 1.64 negative. Step 4, almost there, people. Make a decision on the null whoops, come on, guy, you're too far away. Reject or fail to reject the null hypothesis. So just like we had before, let's draw our curve. Here's our normal curve. It's terrible. And out here we have negative 1.64. Anything on the left-hand side, I am going to reject the null. Anything over here, I'm going to fail to reject the null. So what is our critical value is 1.64. What's our z? Our z is negative 0.96. So if I come down to the mean of 0.96 is going to be about here somewhere. This guy is z is equal to negative 0.96. Therefore, I fail to reject the null hypothesis. Okay. Number 6. Oh, we get a good stretch in. So here we have an exercise guy. Let's scoot this over a little bit. There we go. All right. A fitness course claims that it can improve an individual's physical ability. It should. That's what they do, right? To test the effect of a physical fitness course, the number of sit-ups that a person could do in 1 minute, both before and after the course is recorded. 10 individuals, n is equal to 10, are randomly selected to participate. The results are displayed in the table. Can it be concluded from the data that participation in the physical fitness course resulted in a significant improvement? Improvement. Again, this is not a one-tail test, right? We want to know if something is better than the other. So if our first question is state the null and alternative hypothesis, and I put the null, I put the alternative, what do we want to prove? We want to prove that the mean is greater than 0. Hold on a second. Let's back this train up, because all of a sudden, I don't think we're going to be dealing with our regular t-test, because we've got a little note here that allows you to turn around and say, hey, do this as differences. Let D, the number of sit-ups that can be done after taking the course, be what the difference between what you can do after minus what you can do before. Significance level of alpha is equal to 0.05. I'll grab that over there. But this is giving you a little cheat sheet, and it's telling you, hey, take the difference, take the difference. So we can take this guy's and subtract one from the other. But notice that they're inverted here, right? Because I want this guy minus that guy. So using the magic of computer science, I don't know if this is going to work. Let me cut that. Let me see if I can paste it over here. Yes. Awesome. Excellent. Excellent. So now I'm going to take the difference. 53 minus 36 is 17. 17. 59 minus 49 is 10. 59 minus 44 is 15. 32 minus 22 is 10. That's 3. That's 9. That's 3. 41 minus 28 is 13. 4. 41 minus 27 is 14. Okay? And so this is my D. That's a D. D. And what I really want over here is D bar, right? So let's grab that calculator again. There's our fancy calculator, and put it on the other side for now. And let's add these up. Clear, clear, clear. 17. You can't see the plus sign. I'm going to try to scoot that up. 17 plus 10 plus 15 plus 10 plus 3 plus 9 plus 3 plus 13 plus 4 plus 14 equals 88. 88. So how many observations did I have? N equals 10. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Very good. So this is equal to 88 divided by 10. So that's 8.8 is D bar. D bar. Okay. Kind of got ahead of ourselves there, but I wanted to show the differences before we started writing everything else. State the null and alternative hypothesis for the test. This is obviously a paired sample. So I want to prove, what do I want to prove? I want to prove that participation in the physical fitness course resulted in significant improvement. So D should be bigger than 0. There should have been some improvement from our baseline. Mu sub D should be bigger than 0. Therefore, my null hypothesis is the opposite. Mu sub D should be less than or equal to 0. Excellent. Find the standard deviation of the paired differences. Round your answer to 1 decimal place. Oh, okay. So now we've got to find standard deviation. This is going to be a bit of a pain, but we can do that. We know that D bar is equal to 8.8, and I have all my differences: 17, 10, 15, 10, 3, 9, 3, 13, 4, and 14. And then I take 8 minus 8 as my bar, so this is going to be, let's take that off. Let's do this the long way. D sub I minus D bar, and that's going to be 17 minus 8.8 is what, 9.2, 8.2? 8 and 8 is 16.8. 8.2. 10 is going to be 1.2. 15 is going to be 6.2. 10 is going to be 1.2. 3 is going to be 5.8. 9 is going to be 0.2. 3 is going to be 5.8. 13 is going to be 4.2. Yeah. 4 is going to be 4.8. And 14 is going to be 5.8. All right, so now I want to take that and square it. I'm going to use my fancy calculator for this, but I'm going to do it off screen so we can work a lot faster. 8.2 squared is equal to 67.24. 1.2 squared is going to be 1.44. 6.2 squared, 6.2 squared is 38.44. 38.44. 1.2 squared is 1.44. 5.8 squared is 3. Nope, that's not right. 5.8 squared is 33.64. 33.64. 0.2 squared is 0.04. 5.8 squared is 33.64. Oh, I already did it. 33.64. 4.2 squared. 4.2 squared is 17.64. 17.64. 4.8 squared. A lot of these are negative, right? That one's bigger. 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 And that one's bigger. But you get the point. 4.8 squared. That's not right. 4.8 squared is 23.04. 23.04. 5.8 squared is 33.64. 33.64. Notice that they give you these 5.8, 5.8, 5.8 over and over again. Just go back and grab them so you don't spend so much time. Then I'm going to add these up. I'm going to look for the summation. And again, I'm going to do this off screen. Actually, I can do it. I can do that one on screen. Let's clear this. Make sure you can see the top there. I'll do it on this one. 67.24 plus 1.44 plus 38.44 plus 1.44 plus 33.64 plus 0.04 plus 33.64 plus 17.64 plus 23.04 plus 33.64 equals 250, 20, 250, 20. Now this is, we're going to make sure that they're all the same weight. So finally, when I calculate variance on my way to standard deviation, I divide by 10, and that gives me 25.02. And that is equal to my variance. How do I get standard deviation from variance? Well, standard deviation is simply, standard deviation is equal to the square root of variance. So this is equal to the square root of 25.02, which would be great if it didn't have that little decimal. 25.02 square root is 5. Okay, well, let's go with 5 is my standard deviation. And so this is going to be sigma d. I guess I guess technically it's SD because it's a sample. Okay, so now we compute a test statistic. All right, so how do we compute a test statistic? Well, we don't have very many observations. And so we need to use a t-test for paired differences instead of a z-score for paired differences. Let me make sure I'm in the right place here. And I am. All right. So we're going to do a t-test for paired differences, because here it's better. At this point, it's just a regular t-test. And the reason we're doing a t-test is that my total sample size is 10. Just a second. Where were we? That was a phone call from Tableau, so expect news for your semester projects. All right, where were we? All right, so we have a t-statistic is what we're doing here. And this is just a traditional t-statistic. There's nothing super fancy about it, except that we're going to do it for the differences, which we've calculated. Mu sub whatever it is, mu sub d over the standard deviation of d, which we've calculated, and the square root of the total of observations for d. So again, this is going to be plug and play. I'm going to scroll up and down a little bit here. X bar, do I have a cheat sheet set up? I don't really, do I? No, because we've been developing it as we go along. X bar is the 8.8. Standard deviation was 5, so let's write these down now. X bar D is equal to 8.8. The standard deviation of D was 5. I have my N of 10. What else do I need? I need mu. What was the mu? Mu is 0. Note that we're testing, here it is. Note that we're testing whether or not there's a difference from 0. So mu is going to disappear here in a minute. Let's get some space. All right. So this is going to be 8.8 minus 0. That goes away. It goes to 0. Well, I don't have to. That's superfluous. We don't have to do both. Minus 0 over the standard deviation is 5 divided by the square root of 10. What is the square root of 10? Get my fancy app calculator. Oh, it closed. I have to pay a whole like $7 for this. Come on, fancy calculator. There you are. 10 square root 3.16. I'm going to put that in memory. I'm going to take 5 divided by 3.16, and I get 1.58. So this is, scroll, this is 8.8 divided by 3.58. And that is equal to, fancy calculator, whoops, 1.58, 1.58. 8.8, you can't see that, 8.8 divided by 1.58 is equal to 5.57. Please be correct. 5.57. 6.07. I wonder if that's a rounding issue. It is going to be a big number. Let's go back and do it again. Let's go back and do it again. 10 square root, drop it into memory, 5, it was 5.0 something, right? It was like 5 point, what was the actual number? It was like 5.01, 5 point, whatever it was. Well, actually, we didn't calculate it out that far. So 5 divided by 1.58 is equal to 3.16. Put that into memory. 8.8 divided by whatever's in memory, 3.16, and gives us 2.78. And now we're all over the place. 8.8 divided by, that's not right, it's not 3.16. Let's do it again. 10 square root 3.16. There's our mistake. Put that in memory. 5 divided by 3.16 is equal to 1.58. Put that in memory. 8.8 divided by, recall memory, 1.58 equals 5.57. I get 5.57. I'm pretty sure that's right. That looks like a rounding error to me. We're going to have to work it. When you're doing these calculations, use 4 decimals. The process is right. This comes close to 6.07, and that could be my calculator's only grabbing 4. It's only grabbing 2 decimals. Let me switch it, display 4, and we will see if, and I'll do that later and see if it works better. Determine the decision rule for rejecting null hypothesis. Reject H sub 0 if, what's our stat? Our stat is T, and we want it to know if it's bigger than our critical value. We haven't yet calculated a critical value, have we? No, we have not. So what's our decision rule? Think critical value. How do we get a critical value for this? Well, we need degrees of freedom. That's equals to 10 minus 1. So that's going to be 9. And we have an alpha of, what did they say our alpha was going to be? Our alpha was going to be 0.05. It's up there at the top. Alpha of 0.05. So same thing. Let's go get the book. Let's go get our tables. I don't want chapter 11. I want statistical tables. And I'm going to go until I find critical values of T. And then zoom in. Critical values of T. There we go. Degrees of freedom was 9. If I scoot this over, we can actually see our, let's scoot this over, you can see our stats over there on the right. There we go. Okay, alpha at 0.05, 0.05. Degrees of freedom is 9. That's 1.833 right there. 1.833. So I go and grab my, let's get that completely out of the way. T is greater than 1.833. So we're going to reject if T equals what it is. And this chart looks like this. And there exists a T value of 1.833. And I'm going to reject if it's over on this side. Reject. And then over here, obviously, fail to reject. Do we have a stat? We do. It is 6.07. We calculated 5.57. But again, I think that's a rounding issue throughout our calculations. And it's going to be way over here somewhere, 6.077. So we are going to reject the null hypothesis. That should be over there. Excellent. Finally, number 7. Is that the last one? Yes, that's the last one. Finally, number 7. Consider the following table. What does this look like? This looks like, let me round this up a little bit so that we have, so it makes more sense. Center. There we go. And bring that out. Excellent. This looks like an ANOVA table. So let's consider the following ANOVA table. We have the treatments and we have the error or within treatments and the totals for each. And you know what? Let's build this out a little bit so you have a little bit more space because it can be very confusing in here. There you go. Is that better? That's better. Calculate the sum of squares among the treatments. Please round to the nearest answer. The sum of squares among the treatments. So here's the sum of squares. Here's among treatments. So I'm looking for this question mark right here. Let's call this x. Okay. So x in this case is going to be equal to the total sum of the squares minus the sum of the squares of the error. And that is 4882.92 minus 2031, and that gives us 2851.92. 2851.92. Remembering that x plus 2031 is equal to 4882.92. Let's leave that alone. Next, calculate the mean square among the treatments. Okay, so here's amongst treatments. Here's mean square. Let's call this one y. Y, I don't know. Y is going to be equal to, how can we get this? Well, I have x now, right? So I can go back in here, and this guy is 2851.92. How can I calculate the mean square? Well, if I have these two guys, I can calculate the mean square, because how do I calculate mean square? Mean square of the treatment is equal to SST divided by degrees of freedom, right? And we can take a look at our ANOVA table and see where that fits in. Now, I'm aware that you don't have an ANOVA table in your formula sheet, but you can, if you look at it for a while, figure out where these things work out in terms of equations. So one of the things I would do at the beginning of the test, as soon as the test begins, this will certainly be the case when you're in class, is to draw out your ANOVA table to make sure you've got the right stuff in the right places. In this case, we're looking for the mean square of the treatment, or between the groups, and that's going to be sum of the squares of the treatment divided by the degrees of freedom, k minus 1. All right, so how do I calculate that out? Well, I have the answer, I have the expectation here, 2851.92 divided by the degrees of freedom, which is 8, and that should give me, wait, am I in the right place? I feel like I skipped one. Oh, I did, I skipped 2. All right, well, this is this guy. And let's go get to our fancy calculator. Fancy calculator, 2851.92 divided by 8 equals 356.4. 356.4. So y then becomes 356.4. 356.4, in this case 49. 2 decimal places. You're going to want to make sure we're not rounding. I think my calculator is doing something funny. Let's back up to step 2 real quick. Calculate the degrees of freedom among the experimental error. Well, that's easy. We're going to go up and down with this one. 18 is the total degrees of freedom. 8 of them go to treatments. So this guy has to be 10. 10. 18 minus 8 equals 10. 8 times 10 equals 18. Why do I have a control button hovering on my... Okay. Number 4, calculate the mean square. You know what? Let me grab this whole thing again. Control C, and let's go down here. Oh, you know what? I can't do it with that. but I can do it with my cut tool. Thank you. I want you to grab this whole thing here. Control C. Let's make some space here. I'll put this guy over here somewhere. That's fine. Calculate the mean square of the experimental error. Okay, here's the error. I want the mean square. Let's call this Z. Let's call this Z. All right, so Z, how do I calculate Z? How do I calculate Z? Well, there's two ways now to do it, right? I can take the I can do Z is equal to SSE divided by the degrees of freedom for the error, which is total observations minus K. Or I can also take the test statistic, right, 1.76, and the equation for that calculation, 1.76 is equal to y over z, where y has already been calculated at 356.4. Either one of these will work. I'm going to do the first one because it's just whole numbers and it looks a little easier. So I'm going to use this guy. SSE is 2031. I'm going to divide that by 10, which is my degrees of freedom, and that one's a really easy calculation, 203.1. Effectively, that's what that is. Excellent. Excellent. So now we have a filled out table. What is the sum of squares of the sample means about the grand mean? Please round your answer to 2 decimal places. What is the sum of squares? Number 5. What is the sum of squares of sample means about the grand mean? Well, this isn't a real calculation at all. What this is asking you here is to see whether or not you understand where the sum of the squares comes from. Let me see if I can find it in the book real quick. In an analysis of variance, the sum of the squares of the sample means about the grand mean. So what this is asking is whether or not you understand that what we're doing is taking the sum of the squares and calculating above the grand means, okay? And so we are looking for the sum of the squares for the treatments. This is what we're looking for. The sum of the squares for the treatments. Note that right here I have here's the sums. I take the differences and I take the squares, but I'm calculating these based around the grand mean. That's the X bar is my grand mean. So what it's asking me is, where does this number come from? The sample means is my X bar. About the grand mean means that we're calculating it from the grand means, and that's where the squares come from. We add them all together. So that's SST. Which one of these above here is SST? I think it's time to change colors. Red is fine. Here's SS. This guy X is S, also known as SST. So that's the one we're looking for. We're looking for SS of the treatment. We've already calculated it. It's 2851.92. Again, this question is not mathematics. It's asking you whether you know what it's coming from. What is that? Right, and that is that it's coming from the means of the different samples. What is the variation of the individual measurements about their respective means? Same idea. There's no real mathematical calculation here, but we're asking for the sum squares of the errors. Note that each one of these, when we add them all together, is a single observation. I1, I2, IK, and so on and so on and so forth, separated from their means. The difference between this individual observation and the mean for that particular sample. The sample for this one and that one for each particular sample, and so on and so on and so on. Okay? That's what the question is asking you. What is the variation of the individual measurements about their respective means? The key here is individual measurements. Individual means within And the one that we know is within is the error. So that's going to be 2031. The answer to this guy, where's my, there it is, 2031. That thing's too small. That's why I can't see it. Back to blue. What is the critical value at 0.01? Alpha is equal to 0.01. Round your answer to 4 decimal places. Okay, so how do we calculate critical value? The biggest difference here from the difference here from all the other ones is that this is an F distribution, right? And we know that that's going to look a little different. It technically looks something like that. Okay, and they're always going to be one-sided tests. So we need some critical value here. And what is that going to be at 0.01? Well, that depends. It depends on a variety of things. Let me go back over to our statistical tables. And I want, you know what? I wonder if I have a shortcut to binomial Poisson chi-square. There it is, F distribution. Here's a shortcut to my F distribution. Numerator degrees of freedom, denominator degrees of freedom. Let's go grab those real quick. Numerator degrees of freedom is 8. Denominator degrees of freedom is 10. So this is based off of the numerator, or I should say degrees of freedom for the numerator and the degrees of freedom for the denominator. So this is going to be 8 and 10. Okay. That's not really a fraction. Don't divide this. I should say 8 and, or a comma, and a 10. 8 and 10. All right, so let's go back to our critical values. Numerators and denominators. And I think we can do it here on the first page. 8 and 10. Oh, because this is at 0.10. I don't want 0.10. I want 0.01. 0.10, 0.05, 0.025, 0.025, 0.01. Yes. Let's zoom in so we can have some fun with this. Let's zoom in so we can have some. Let's zoom in. So we can, I can't really do this with this. Can I drag this over here? I cannot. I'm going to pause for a second. Okay, found it. And I was actually on the previous page. So I go back to the F distribution. I make sure that I'm at alpha equals 0.01, which is what the test is asking me. And I calculate the numerator degrees of freedom. I know that's 8 right here. And I look at the denominator degrees of freedom. It says over here on the left-hand side, denominator degrees of freedom. And I know that's going to be 10. So I go 10 to 8. Again, 10 to 8. And it's 5.0567. That's my answer, 5.0567, because the numerator was 8 degrees of freedom and the denominator was 10 degrees of freedom. And this chart only works because alpha is 0.10. So I forgot to actually write it down. 10, 8, 5.0567. So what is it? It is 5. Oh no. It's not at 0.01, it's at 0.10. Again, basic but critical mistakes. Got to fix those. Got to be ahead of the curve here. Let's back it up, back it up, back it up, back it up. Zoom in, and let's do this again. Numerator degrees of freedom, denominator 8 and 10. The answer is 2.3772. 2.3772. Excellent. Excellent. All right, let's keep going. Is the test statistic significant at 0.01? Well, let's go ahead and draw it out real quick, and we'll double check it. Okay, looks like we're almost done. So we have this curve with an F distribution that looks like this. It's a one-tail test all the way. And we have a critical value, or a critical test at a critical value of 2.3772. If I am north of that, I'm going to reject. And on this one, I'm going to fail to reject the null hypothesis. Where is my test statistic? Where is my test statistic? Here is my test statistic, 1.76. It is also known as the f-stat, 1.76. So let's go back to our curve. Let's go back to our curve. There it is. 1.76 is going to be in here somewhere, 1.76. Therefore, I fail to reject. Is the test significant at 0.01? No, it is not significant. Not significant. And we are done. That was a little longer than expected, and you saw me make some very basic mistakes that students make in the exam. Happens all the time. Hopefully, when we make these mistakes together, you guys can figure them out. I apologize for the video. It's a little longer than I expected it to be, but have fun studying. Good luck. I will send additional instructions.